Chaowei, and I'm going to present our paper titled From Patching Delays to Infection Symptoms Using Risk Profiles for an Early Discovery of Vulnerabilities Exploited in the Wild. This is a joint work with Chaowei Xiao and Mingyan Liu from University of Michigan, Yang Liu from Harvard University, Bo Li from UIUC, and Tudor Dumitrash from University of Maryland. So software vulnerabilities represent a very valuable resource for attackers. Once a vulnerability is discovered, this essentially triggers a race where attackers can try to develop exploits, which then they use to launch attacks. At the same time, software vendors try to develop patches which end users and enterprises then install on their machines to secure them. But resource constraints and also user tardiness can introduce delays in the installation of patches, which then creates windows of opportunities for attackers to exploit them. It is estimated that on median only 14% of vulnerable hosts are patched when exploits are made available. We saw recent examples of this in the WannaCry and NetMedia outbreaks and also the Equifax data breach. In all these cases, the underlying vulnerabilities had been patched months before the incident, but since a lot of hosts had not installed them, this eventually led to the success of these attacks. At the same time, only a small portion of vulnerabilities are ultimately exploited. So if one can try to rank order vulnerabilities by severity, meaning if we can predict or detect whether they're being actively exploited, this allows one to prioritize patch deployment for these more severe vulnerabilities. In an ideal world, one would like to install patches as soon as they're available, but we live in a resource-constrained world. And this ability allows one to secure their machines more effectively using resources that are available to them. So what's the current state of exploit detection? There's work that focuses on intrinsic or a priori vulnerability attributes, such as where it can be used to take remote control of a host. However, as we show and others have shown, these are not strong predictors of eventual exploitation, since they don't take into account any real-world data. There's also work using crawling social media sites to detect exploitation, but these typically only provide a few days of lead time, since they ultimately rely on a human to detect exploitation. So our contribution in this work is to develop a method to look at real-world measurements and try to extract statistical evidence of exploitation. We show that combined with intrinsic CVE attributes, these real-world measurements can achieve a 90% true positive rate with a 10% false positive rate using only 10 days of post-disclosure observations. For comparison, in our database, the median time for exploit detection or the reports of these exploits is 35 days. So we're doing this 25 days prior to current detection times, which provides large lead times for prioritizing patch installation for these critical vulnerabilities. So to provide a simple an overview of our methodology, let's assume that we have different strains of a virus that can be active at an area. One works through air contamination, the other through water contamination. And we can observe subpopulations that are susceptible to these factors, which we will call risk behavior throughout the rest of this presentation. By looking at these patterns and comparing them to the infected population or the symptom patterns, we can then try to statistically determine which strain is active. In this analogy, then different strains correspond to different software vulnerabilities. In practice, though, this direct comparison doesn't work for our data for a few different reasons. One is that infection can be caused by many different vulnerabilities, and the sheer number of them dilutes our signals, which hides the association between risk behavior and symptoms. On the other hand, infection doesn't work immediately. Once someone is vulnerable, it takes an uncertain amount of time for them to be infected and show up with symptoms. So what we do instead of directly correlating risk behavior in symptoms, we use the simple heuristic that if we look at similar entities or ISPs that we use for our study, if we look at similar ISPs in risk behavior, and the underlying vulnerability is actually being exploited, then the similarity will transfer to the symptoms that we observe. So like I said, instead of directly correlating symptoms with risk behavior, we look at similarities in their similarities. And this is done by applying community detection and comparing the community structure of symptoms with risk behavior, which then allows us to quantitatively measure the association between these two signals. So to go over the data that we use for our study, for symptoms we use different spam blacklists. We combine 5 different spam blacklists. The idea is that once someone is infected, once a host is infected, then a portion of these infected hosts will be used as bots to send out spam and eventually detected by these lists. This is not a perfect proxy for infection, but as long as a portion of these infected hosts are being used to send out spam, we will detect this similarity transference basically, and we show empirically that it works reasonably well. For our risk behavior signals, we combine patching data for 7 different applications from Symantec's Wine dataset. This includes patching data for 5 different browsers, Adobe Reader and Adobe Flash Player. We combine these with publicly available vulnerabilities or CVEs from the National Vulnerability Database. By combining these, we can then obtain for each CVE participating hosts that are susceptible to these CVEs at any point in our observation period. For ground truth signals, we also collect real-world exploits from 3 different sources. This gives us 56 exploited in the wild and 300 non-exploited vulnerabilities. We then use these as ground truth labels to train classifiers that will try to detect exploitation and report our performance using these ground truth labels. So to go over our data processing, we first aggregate both symptoms and risk behavior over ISP boundaries. So this then gives us 2 signals for each CVE, the number of hosts that are susceptible to the underlying CVE at any day within the ISP that we're examining, and also the number of infected hosts within that ISP. And for the 10-day time window following the vulnerability's public disclosure, we compute these signals and compute their pairwise similarities. This then gives us 2 similarity matrices for any CVE, one for symptoms and one for risk behavior. We can also think of these similarity matrices as weighted graphs, where the weight of the link between 2 ISPs in this graph quantifies their similarity. Here, for instance, we see that the first 2 ISPs are highly correlated, while they don't show a lot of correlation to ISP3. So once these graphs are obtained, we then apply our methodology, which I introduced in the introduction. We apply community detection to extract groups of ISPs that exhibit similar symptoms for the 10-day period following each vulnerability disclosure. So, like I said, what you can do is we can extract communities from both symptoms and risk behavior and put them on top of each other to try to see whether the same community structure applies to both, which would help us identify associations between these 2. But instead of applying community detection twice, which can be computationally intensive, we only apply it once to symptoms, and then we try to evaluate the risk behavior signals over this obtained community structure to see whether there is any association between the 2. We do this by defining 2 types of links in our graph using the community structure obtained from symptoms. Intercluster links are those links between ISPs that reside within different clusters. Intracluster links are those for ISPs that reside in the same cluster. By definition, a community detection algorithm tries to maximize the difference between intra-cluster and inter-cluster similarities. So by looking at these two similarity measures for risk behavior signals over the communities obtained from symptoms, we can then try to see if the same structure applies to risk behavior signals as well. So here I have an example for two different CVEs. So to summarize, we compute intersimilarity and intrasimilarities of risk for any pair of ISPs in our data, and then plot their distribution or cumulative distribution, their CDF, to try to see if there's any distinction between these two. On the left here, I have an example for a non-exploited CVE. We see that there's little distinction between these two distributions. Means that none of, basically, since it's non-exploited, none of the vulnerable hosts are actually being infected. So there's no association between the two signals. But when we look at an exploited CVE on the right, we see that intra-cluster similarities are decidedly higher. This means that the community structure is now being transferred between the two, which would give us statistical evidence of exploitation. So I've shown our conjecture here is that the higher intra-cluster similarity is an indication of active exploitation, but this is just an example for two CVEs. To evaluate this for all of the ground truth data in our data set, what we do is we take basically the difference between the green and the red curves here and feed it to a supervised classifier, which then tries to tell us whether the vulnerability is being actively exploited. So what I just described gives us a feature set that we call community features. But we also compare with different feature sets that we extract from real-world measurements. We use the raw risk and symptom similarity matrices for comparison, and we also use histograms of the correlation between the two similarity matrices as well. And we call these raw and direct features. Direct features basically forego the community detection step, but we show that they're inferior in predictive power to the community features. Finally, we also use intrinsic attributes of CVs themselves. Like I said, these are not strong predictors by themselves, but we actually see that they complement our real-world measurements very well. We use tokens extracted from vulnerability descriptions, such as the word remote that can be indicating that the vulnerability is being used to remotely control a host. CVSS scores that summarize the severity of these vulnerabilities. And then we use different combinations of these feature sets and train random forest models using our ground truth data. To prevent overfitting, we use 5-fold cross-validation and average the performance of our models over 20 different rounds. So on the right here, I have the ROC curves, or the true positive versus false positive rates of different classifiers trained on different combinations of features. The best classifier uses all features. As an operating point, we observe 90% true positive rate versus 10% false positive rate. We can also measure the area under these curves, which gives us the overall, which quantifies the overall accuracy of the model, called the AUC, or area under the curve score. Using all features, we observe a 96% AUC. Using only community and intrinsic features, however, we observe a 95% AUC, which is very close, meaning that most of the predictive power of our data is just summarized between these two feature sets. Interestingly, we see that when looking at community features alone, we achieve an AUC of 76%, which is still better than random guessing. Note that random guessing would give us an AUC of 50%. But it shows that this is using just community features is prone to misdetections and false positives. This can be due to noises in the data, which I will explain in a bit. But when combining the two, then we also allow our algorithm, the supervised classifier, to fall back to intrinsic features and also use those as further validation. For instance, if we see weak indication of exploitation using the field measurements, and we also see that the intrinsic attributes are not indicating a severe vulnerability, then maybe this is a false alarm. But if we see some indication and actually intrinsic features are telling us that this is very severe, then it can be further validation that this vulnerability is actually being exploited. So what I just presented, like I said, uses 10 days of post-disclosure data. But we can basically move this window to any point in time. We can apply it right on the disclosure date to see whether the vulnerability is already being exploited when it's publicly disclosed, indicating zero-day exploits. We looked at some case studies for these. For instance, we saw examples such as this Adobe Acrobat Reader CVE, which was actually reported as a zero-day exploit, and our system was correctly detecting using community features. We also see some CVEs that are not reported as zero-day. This Adobe Flash Player example was reported to be exploited months after the public disclosure date, but we saw some indication of active exploitation right on the disclosure date as well. This can indicate that some of these vulnerabilities, and I also mentioned this in our introduction, that some of these vulnerabilities are being actually exploited much before what was at the time being reported, and I think this is a very interesting result. So I've talked about the practical utility of our method. It allows enterprises and also end users to prioritize patch deployment for critical vulnerabilities and also to assess their own risk. Some secondary uses are for software vendors to develop patches for critical CVEs faster, and also ISPs to identify at-risk populations and encourage prompt action. So our methodology is prone to a few data imperfections. Spams are not a perfect proxy for infection. Not all spam is generated by infection. Some servers can actually be rented to send out spam, and not all infections result in spam. At the same time, aggregation can lead to averaging out behavior, which could otherwise be used to detect exploitation. However, we see that even in the presence of these, when we combine our real-world data with intrinsic attributes, it allows the model to fall back to these attributes to build a more robust system. However, it would be interesting to see whether addressing some of these issues can help us achieve better accuracies. So to conclude, we have shown a method for achieving a true positive rate of 90%, a false positive rate of 10%, using 10 days of post-disclosure observations. The current median time for detecting these exploits is 35 days, with 80% of them actually being reported beyond 10 days. This can indicate that a lot of these vulnerabilities are actually being exploited before what is reported in our data sets. And we also see that combining intrinsic and real-world data in the form of community features results in a robust classifier. Some future directions include appending additional data sets of symptomatic data to build a more robust data set. We can, for instance, include DDoS sources to include other forms of infection. Also, applying this to other domains such as internet scans to identify at-risk servers or even IoT devices is another way to extend this work. Thank you for listening.
All right, time for questions. To get this started, I have a question. So your approach promotes the patching of vulnerabilities that are currently being exploited in the wild, right?
Yes.
So is this likely to indirectly cause some other vulnerabilities to be forgotten, to the ones that are not being currently exploited?
Okay, yes, yeah. I did mention that ideally one would like to patch vulnerabilities as soon as they're reported, right? But the truth is that we live in a resource-constrained world, and this is not possible. So I think that this would allow more effectively securing machines because you're focusing on those that are being exploited. But this actually has to be implemented to see maybe by doing this you're actually encouraging attackers to move on to other vulnerabilities to exploit. So I think unless we actually implement this in the real world, we can't say for sure.
Right. In case we don't have a question, I have another question. So intuitively, it feels that the vulnerabilities that will be exploited first are generally going to be the ones that are easy to exploit. Right. So have you thought about prioritizing vulnerabilities further based on how severe they are and stuff like that?
So I think what you're mentioning is actually the intrinsic attributes. So some of these, so there are CVSS scores that actually tell you how, I don't know if they tell you how easy it is to exploit, but they basically tell you whether it's possible to exploit these. For example, for remote access and so on. And these are not generally strong predictors because there's a large number of vulnerabilities and attackers don't choose all of them. They randomly choose one to exploit, right? And so I think we show that actually you have to combine this with field measurements in order to see which one of these more severe vulnerabilities actually being exploited.
Yeah, so just to provide a to add to Armin's answers. So, in addition to the prioritization application for this technique, this is a way to compute the risk that each vulnerability presents, because different vulnerabilities have different risks, and to compute it based on data rather than subjective assessments by analysts, which say this might be more exploitable or more severe.
Thank you. Let's thank the speaker.